In this video, we'll cover the ratio test. So the ratio test is probably one of the most popular tests to use to show series convergence. Obviously, as with all other series tests, there's no guarantee that it can be applied, but it is definitely a popular series test. So let's take a look at what it is. Let's say that our series, we'll call it a sub n, is a series with non-zero terms. We will compute the limit as n goes to infinity of a sub n plus 1 over a sub n. And we'll get a finite, possibly, limit. So there's three possible cases that this limit could be. If the limit falls between 0, less than or equal to the limit, less than 1, then our series converges absolutely. If our limit is greater than 1 or limit is infinity, then our series diverges. And lastly, if our limit is equal to 1, the test does not provide any information. So our third case is the case that tells us that we have to then move on to another series test to determine anything about the series. So one thing to note is that when we say that the series converges absolutely, if you've taken a look at the alternating series video, you'll see that when a series converges absolutely, that means the original series also had to converge. So this implies just general convergence as we know it. Okay, let's take a look at some examples. So for each of the following series, we'll use the ratio test to determine whether our series converges or diverges. And our first series will be the series 2 to the power n over n factorial. So to get started, we take the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial. That's the a sub n plus 1 term over now the original 2 to the n over n factorial. And we didn't really have to write that things are non-zero because 2 to the n can't be 0 and n factorial obviously can't be 0. It's worth reminding yourself that n factorial is equal to n times n minus 1. You basically count down to 1 doing the product of the numbers. So it means take whatever number you see and multiply all the numbers smaller than that number times that number. So n factorial, not going to be 0. 2 to the n, not going to be 0. That means that we can go ahead and, we've checked that our series has non-zero terms, so we can at least compute this limit and see if our test is helpful. So when we simplify, this becomes, everything's going to be positive anyway. So we can drop the absolute values, and we end up getting 2 to the n plus 1 in the numerator over n plus 1 factorial times n factorial over 2 to the n. And we can simplify the exponentials, and then we can simplify the factorials. So when I look at what n factorial over n plus 1 factorial is, what you want to think of is, let's say we had 5 factorial over 4 factorial. 5 factorial over 4 factorial would give me 5 times 4 times dot 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 times 1, and 4 factorial would give me just the 4 part. So that means that this would simplify to just the 5, right? So that means that in general, this is going to simplify to just an n in the denominator, and 2 to the n plus 1 is bigger than 2 to the n, so there's just one 2 on top. Pardon, we're left with an n plus 1 in the denominator because that's the actual biggest number. Okay, so computing the limit as n goes to infinity of 2 over n plus 1 is going to be 0. So if we look back at our cases, we ended up with case 1. Our 0 is less than or equal to our limit is less than 1, so our series converges absolutely. Okay, so by the ratio test, our series converges. Let's look at another one. For our next example, we'll determine whether n to the power of n over n factorial converges or diverges. So all of our terms are going to be non-zero. N is greater than 1. Okay, so that's really all it takes to apply the ratio test. N to the power of n plus 1 over n plus 1 to the power of n plus 1 over n plus 1 factorial over now the nth term, n to the n over n factorial. And all of that's inside the absolute value bars. Okay, since our n is always positive, we can drop out the absolute value bars. We will be left with the limit as n goes to infinity of n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n, which this simplifies to, if we take a look at n plus 1 factorial and n, we'll be left with an n plus 1 in the denominator, and we'll be left with n plus 1 to the n in the numerator. We can't merge that with the n to the n because it's a different base. So, but fortunately, we can actually reduce the n plus 1s. So you have n n plus 1 to the n plus 1 over n plus 1 gives you just n plus 1 to the n. And that's over n. So we can write the power like so. And we can simplify this fraction to, I can write that as the limit as n goes to infinity. N over n is 1 plus 1 over n to the n. Okay, this is a very common limit. I'm going to give you a second to look at that. This is a very important special limit. It's actually the definition of something. Limit as n goes to infinity of 1 plus 1 over n to the n is actually e. That is how we describe the definition of what this constant e is. So it's cool to see how that can pop up out of seemingly nowhere, right? So we've got a finite limit, but it's not between 0 and 1, so we're not in case 1 anymore. It looks like we're in case 2, limit greater than 1. So it means that our series diverges. Okay, so by the ratio test, our series diverges, and that's all we need for showing divergence. Let's take a look at another example, one more. This looks like it's an alternating series, negative 1 to the n times n factorial squared over 2n factorial. The ratio test will tell us if it converges absolutely, and if it converges absolutely, then we don't need to do the alternating series test because we can just conclude that the original series would also have to converge. So let's apply the alternating series test first because n is greater than or equal to 1. Terms are non-zero. That condition is met. Now we'll take the limit as n goes to infinity, taking the absolute value. In this problem, the absolute value is actually going to help us simplify our series. 2n plus 1 factorial over negative 1 to the n factorial squared over 2n factorial. Pay attention to where your parentheses are. This is going to clean up into the negative 1 to the n's are going to be canceled out because this absolute value bars will make the terms positive. So we'll just be left with limit as n goes to infinity. We'll have the n plus 1 factorial times n plus 1 factorial over 2n plus 2 factorial times 2n factorial over n factorial times n factorial. So we're splitting up the squared terms just to see how they're going to reduce here in the next step. Looks like in the denominator we'll be left with 2n plus 2 times 2n plus 1 And those can cancel out. The n plus 1 factorial will pair up with the n factorial, leaving us with n plus 1 times n plus 1, which this ends up being a nice polynomial. It ends up being the limit as n goes to infinity of n squared plus 2n plus 1 over 4n squared plus, let's see, 4n, 6n plus 2. And we can factor out the n squared to leave us with 1 plus 2 over n plus 1 over n squared for the numerator, and denominator n squared times 4 plus 6 over n plus 2 over n squared. And the n squareds eliminate, and pushing the limit through, we'll see that all the terms head to 0 except the 1/4. So our limit is just 1/4, and we have our limit is between 0 and 1. So by the ratio test, our series does converge. The ratio test is perhaps, just besides being the most popular test, I would say it's possibly the most important of our convergence tests. So I strongly recommend that you pay close attention to this entire section and all problems that you're practicing on. We will be returning to the ratio test within our next unit of power series quite a bit. So it's definitely good to practice this a lot. And I'll see you next time.